Hi everyone, welcome again to the course of structural biology. We are going through the module of visualization. I have given you the details about the journey of how modeling visualization started with the initial development of the physical model to the sophistication of the model to the sculpturing and ultimately to the introduction of the computer, and today it is really have achieved a place where very high resolution pictures are available, high resolution movies are available, which are helping the scientists, the educators, the researchers and even the students to understand biology in a real easy mode. But there is a process. What I mean, you cannot talk to the computer. So, today we will talk about that. Today we will talk about the database of structures of biological macromolecules. In the last module, I have already talked about the protein data bank, which is considered as the database of 3D structure. But in that database, how the files are there, what type of files are there, and especially the coordinate files, which are the main to give us the 3D information of the atoms. We will understand that in this class. So, I have talked about protein data bank. I have also talked how different databases, the NMR database, the cryo-electron database, the other databases like nucleoside database NDB, and different part like PDB-E, the PDB from Europe, the PDB-J, the PDB from Japan, all coming into a common database or data bank, which is called protein data bank, RCSB PDB. If you look at the current holdings of the protein data bank, only protein entries are 1,36,983 by solving through X-ray structure. NMR, it is 110613, electron microscopy 4725, and other multiple method 166, neutron diffraction 67, other 32, which are coming into small methods. So, total of 1,53,586 protein molecule already have entered in as a structure. Protein oligosaccharide 8093 for X-ray, 31 for NMR, EM 655 a significant change. Protein nucleic acid 7226 in X-ray, 217 NMR, and very significant number 1632 in electron microscopy. And this field, this protein nucleic acid, because these are talking about big complexes, ribosome is one of them, I am sure electron microscopy is going to surpass. Anyway, we have already talked about that 1,75,282 entries are there. But before going into the detail about the PDB, I want to talk about few things which are very important. If you remember, our journey started from sequence to function, and I told their structure is required. So, when we see here 1,53,586 proteins, only protein I mean, 1,53,586, do they represent that many proteins? Do the structural entry of 1,53,586 protein represent 1,53,586 protein? The answer is no. Why no? Because there are many proteins which are important because of therapeutic reason, because of other reason like their antibody or their important structural protein and all these things. So, kind of 30,000 I would say unique proteins would be available. So, this is a knowledge. Another knowledge, initially when the journey of structure determination was started, for protein, when we say the structure to function, the important thing is fold, how the protein is folded, and that is why it is critical to go from a journey of a sequence to structure. Now, you would be very surprised or you will be very excited to see that the appearance of new fold reduces with the increased appearance of new structures, and currently every year if you see, we have actually no new fold or very little modification in existing fold, or a permutation combination of 2 or 3 fold coming into one structure. So, this is a great thing because with the next generation sequencing we now know that every day thousands and millions of genes are actually appearing, which means millions of proteins, but if they correspond to just few folds, then the predictions would be easier, our computational tools would be more accurate, and the requirement of structure determination would become much less. Keep it in mind, that would not reduce the importance of structural biologists, because you need new structures because of different reasons. Like when you want to do a drug designing, you definitely need to know the high resolution interaction between the protein and drug, and you need crystallographers to work on them. If you want to go for high resolution structure of the bigger complexes, you need electron microscopy. When you need the dynamics of the small proteins, peptides, you need NMR. But with less number of novel folds coming, the accuracy of computational prediction will definitely enhanced, and that would help us controlling and determining more and more structure through computational prediction. So, first you need to get the Pdb file. This is the home page of Pdb. First you have to search Pdb file, and for that, if you remember, you have to use a 4-letter number combination, which is called a Pdb code. I would like to refresh your knowledge about a Pdb code gives unique code for a structure of protein, which means one protein could have many Pdb IDs if that protein have more entries here. Why it would need more entries? Remember, just in the last slide I talked about, if a protein is important, like a protein I work on which is called beta lactamase. Beta lactamase is a very important therapeutic protein. So, people need to understand about beta lactamase. So, they have tried to get its structure from different organism, they have tried to get the structure with different ligands, drugs, and currently you will get thousands of structures, not single, thousands of structure of beta lactamase. So, unique code is Pdb ID, but there is something called UniProt ID. This is unique for one protein. So, if you have beta lactamase from E. coli, the TIM, it would have only one UniProt ID, but it could have many PDB IDs. You have to understand that. So, you incorporate the unique PDB ID, which is unique for a structure, give a search and then you will. So, here you put the PDB ID. I have given search for 3HP1 and you will come to the information. This is crystal structure of human DCK R104M, which is the information of a mutant, D133A another information of a mutant in complex with LDT means L-deoxythymidine and ADP adenosine dinucleotide phosphate. So, you see the entry and there are two options to look at the file. One option is display file, another option is download files. Through display files you could see the files, to download files you would download the files. When you go to display files, there are three major group of information. One, the FASTA sequence, two, the PDB format, which is in 2 ways: PDB format header and mmcif format. PDB format I talked about and I would discuss in detail at the end of the class. So, now I would discuss about FASTA sequence file and mmcif format. FASTA format. In the field of computational biology, the FASTA format is a text based format for representing either nucleotide sequence or amino acid sequences, in which nucleotides or amino acids are represented using single letter code. So, FASTA format is a format which is a globally used standard format to write your protein or nucleic acid sequence. The format also allows for sequence names and comments to precede the sequences. The format originates from the FASTA software package, but has now become a near universal standard in the field of computational life science. As I told, FASTA is good because we all use FASTA. So, any of the format, when you talk about this, you should remember any format, you cannot say this is a good or bad. If a lot of people around the world start using them, that format, it would become a universal format and it would be easy to talk in that language. We talk in different language, but it is a universal norm kind of when we meet worldwide people who speak in English. It is same as in international unions have decided rules how to talk, how to write a compound globally, IUPAC. The IUPAC rules decide how you call a compound. You call it Ram, Sam, you call it Dick, Harry, you call it anything, but there should be a universal name where everyone recognize. FASTA format is kind of becoming a universal format representing the sequences. What is the reason? The simplicity of FASTA format make it easy to manipulate and parse sequence. Parse sequence means parser is a kind of, you could say, program which extract information. So, when you want to extract sequence information and the information is in FASTA format, it is easy. So, the simplicity of the FASTA format makes it easy to manipulate and parse sequences using text processing tools and scripting languages like R programming language, Python, Ruby, Perl, all the commonly used languages. The original FASTA or Pearson format, it is also alternatively called Pearson format, is described in the documentation for the FASTA suite of programs. You could download it with any free distribution of FASTA. The format and all are I have written for you. In the original format, a sequence was represented as a series of lines, each of which was no longer than 120 characters and usually did not exceed 80 characters. This probably was to allow for pre-allocation of fixed line sizes in software. At the time, most users relied on Digital Equipment Corporation or DEC VT220 terminals, which could display 80 or 132 characters per line. So, to match with them, it had no longer than 120 character and usually not exceeding 80 characters. Most people prefer the bigger font in 80 character modes, and so it became the recommended fashion to use 80 characters or less, often 17 FASTA lines. Also, the width of standard printed page is 70 to 80 characters, that also helps. So, as a result, 80 character become a global norm. The first line in the FASTA file started with a greater than symbol, or sometime a semicolon was taken as a comment. Subsequent lines starting with a semicolon would be ignored by software. So, if you want to write some information for your understanding regarding the sequence, if you do this, then software would not read them as a part of the sequence. Since the only comment used was the first, it quickly became used to hold a summary description of the sequence, often starting with a unique library access and number, and with time it has become commonplace in always use greater than for the first line and to not use semicolon comments. Following the initial line used for a unique description of the sequence was the actual sequence itself in standard one letter character string. Anything other than a valid character would be ignored, including spaces, tabulators, asterisks. It was also common to end the sequence with an star asterisk character, and for the same reason to leave a blank line between the description and the sequence. This is the FASTA format representation of the protein corresponding to the PDB ID 3 HP1. If you see, it starts with a greater than sign, it ends with the asterisk sign, and the description is here. This line is not considered as sequence or as part of the sequence because of the greater than. You put greater than, you could write more things here. Next sequences are giving amino acid sequence, M, G and all these things. So, M is for methionine, G is for glycine, and you get the entire sequence of the protein which is used for structure determination. Coming to the second one, the mmcif. But before describing mmcif, I would describe CIF file. CIF files are more popular, mostly used in any crystal information. So, it is called crystallographic information file or CIF. The crystallographic information file is a standard text file format for representing crystallographic information promulgated by the International Union of Crystallography, the IUCR. As I told, all those standard files which are used globally, they have some universal rules behind them, and crystallography information file, the rules are made by International Union of Crystallography, the IUCR. CIF was developed by the IUCR Working Party on Crystallographic Information in an effort sponsored by the IUCR Commission on Crystallographic Data and the IUCR Commission on Journals. The file format was initially published by Hall, Allen and Brownen, has since been revised, and the most recent version is 1.1. Full specification for the format are available at the IUCR website. Many computer programs for molecular viewing are compatible with this format, including JMOL. mmcif, which is of our interest, is macromolecular crystallographic information file. So, the term is for macromolecular, then for crystallographic information file. So, mmcif, mmcif. Macromolecular crystallographic information file, which is intended as an alternative to protein data bank format. So, as I told, we talk about PDB format, we are going to talk about PDB format even in more details, but mmcif is an alternative to protein data bank format. It is now the default format used by protein data bank. Also closely related is crystallographic information framework, a broader system of exchange protocols based on data directories and relational rules expressible in different machine readable manifestations, including but not restricted to crystallographic information file and XML. So, there is interconvertible option and that makes the use more broader. This is the link where you could know more about the mmcif. mmcif is a flexible and extensible tag value format for representing macromolecular structural data. The set of mmcif tags which determine the classes of information present in a given mmcif format file are defined in an mmcif dictionary. The structure of the dictionary is in turn defined by DDL. The standard mmcif dictionary, now stable since being ratified by the IUCR in 1997, was pioneered by Paula Fitzgerald, Helen Barman, Phil Borney, Brian McMahon, Keith Wattenpug and John Westbrook. However, work is still going to improve. This is the link of the mmcif file of the protein whose unique structure is provided by the PDB ID 3HP1. Coming to the downloading. So, there are two options, display file, download file. The download file option is more vivid. Here we have FASTA sequence format, I have already talked about. PDB format we have discussed, PDBX mmcif we have discussed, PDB ML, XML another alternative, biological assembly. So, if the protein is oligomeric, when you look at the coordinate you see the file, but the actual biological assembly is expressed here. Then we have the structure factors, we have validation, we have maps. I will just talk about two things, one is validation because that is very important and another is map, which I will discuss in next class in detail when I would include the actual MTG file and use it in the CUT format, but here I will little bit introduce you to you. So, coming to the MTZ file, an electron density map can be read from CCP4 map file or an MTZ experimental data file. So, up to now we are talking about PDB, mmcif, PDB XML, they are all giving structures, whereas MTG is a different one which is giving the information about the map. If you go back, you will see, if you remember, the F0 FC map and 2F0 FC map. I have talked about them in the crystallography section. Loading an MTG file is slower as the map needs to be calculated, but there is an option to recalculate the map with a different grid spacing which can be useful in creating the optimum image. Other experimental data format can be converted to MTZ using the convert to MTZ and standardized task in the CCP4I interface in the CCP4 modules. This can be found in reflection data utilities module. This is the representation. So, if you look at this window, that is how the window appears when it have to read a MTG file. Going here, you need to select structure factor, the F and the structure factor and the phase column data and optionally weight column data to calculate the map. So, weight column data to calculate the map. The default map grid size of 0.75 angstrom is appropriate for model building work, but a higher resolution may give a better picture, but slower performance because more high resolution, more calculation. If the setup as difference map option is on, then the map will initially be drawn with 2 contour level with plus minus 3 sigma. If there are models loaded, then there is an option to specify which model is associated with the map. This model will then be treated as part of the crystal and symmetry related models will be generated. So, what it is talking about, suppose you have this electron density and you have 2 Pdb, this is a tyrosine suppose, and this is here, and there is another tyrosine coming from another structure. So, if you specify, then the map will take proper space. It might be shift from here to here. If you specify which one is the structure, it is the A structure or the B structure, the structure which is assigned, the model which is assigned for the map will go and fit it. So, that is what you could see. After the map is loaded, the map data object is listed in the display table and a crystal object is also listed. This object is mostly concerned with the display of the model in the crystal and is described. So, when you look at that, you would be looking that the map would now guide you towards the further model building, making the model complete. That is where the role of the MTZ file. Validation report is very important, and incorporation of validation report. The validation report was not there at the initial protein data bank, and when I say initial, it was actually incorporated after a long time. So, if you look at the initial page of the validation report of 3HP1, you will see that the 3HP1 was deposited on 2009, but the validation report make on May 23, 2020. So, now probably you understand what I am saying. The incorporation of validation report came much later, but these have changed a lot in the world of structural biology. Incorporation of validation report have helped or guide the user towards modification of the initial mistakes, and when the user have taken care of that, and when PDB actually agree to the performance of the structural biologist and agree to provide a validation report, the quality of structure is significantly improved, which is further improving the quality of computational biology work. So, in one word, the introduction of validation report is a revolution. There are many aspects: entry composition, residue property plots, data and refinement statistics, model quality, fit of model and data. A lot of things happen. I just keep this, select this for giving you little details: the entry composition where everything is there, and data and refinement statistics. But residue property plot, working on individual residues, how they are plotted, how they are fit, they are in agreed position in terms of Ramachandran plot and all. Model quality is checking how the model quality is in comparison to other published structures, and fit of model and data is fitting it with considering different macromolecules and all. So, as I told, overall quality at a glance here, the following experimental techniques were used to determine the structure: X-ray diffraction. So, the technique is given, the resolution is 2.31, the resolution is given, the percentile core for global validation matrix of the entry are shown in the following graphic. So, if you see where it is ranked, you see from worst to better. So, you will see the position of the structure. Then in the metric, and you have class core, Ramachandran outlier, side chain outlier, RSRZ outliers. Also the table here you see, you could see the summary of geometric issues which observed across the polymeric chains and their fit to the electron density. So, where you see the green is actually better, and you could see the all the reason of the colorings. Coming to data and refinement statistics, here space group, cell constants, resolution, percentage data completeness, R merge, R sim, signal to noise, I by I6 sigma, refinement program, R free of the test set, Wilson B factor, anisotropy, bulk solvent, L test for twinning, estimated twinning fraction, F0 Fc correlation, total number of atoms, and average B factor is given. Some of them are coming from the depositor. So, I was the depositor of the structure. So, these are informations coming from me, but then some are also tested, if you see, by the electron density server, and others are coming from either electron density server or PDB or X-triage. So, day by day now most of the informations are getting better, like sometimes the information is not good, not because the actual quality of the structure is bad. I am talking about the old structures, because those factors were not taken care, might be one of the reasons. And now when we are checking it for new structures, we check all the factors before even the final deposition and entry. So, now we get the PDB 3HP1.pdb and we save it to files. So, you could do the PDB format or in the format where the data, because it is a big data, right, reduced, okay, in zip or anything. Now, we will come to how to read a PDB file, which I told the most important part. The general information, the following describes the minimum coordinate specification in PDB format that is required by the RCSB validation and deposition. What are they? Each line is 80 columns wide and is terminated by an end of line indicator. The first 6 columns of every line contain a record name. This must be an exact match to one of the stated record names described in the detail below. So, in the detailing, whatever you are doing, you have to record them. The list of atom records in each polymer chain must be terminated by a third record. Atom records for polymer atoms must be include non-blank chain ID fields. To use the automatic validation check, the coordinate file must include a complete CRYST1 record defining the unit cell and the space group information. If an alternate setting is being used for the space group symmetry, then the orthogonal to fractional transformation must be specified in scale records. Each file should terminate with a line containing only the word end. If atom names of het atom residue names are unrecognized in the dictionaries, validation result will not be optimal. So, what are they? You heard the rules, but now I will explain it going to the actual PDB file. So, this is a PDB file, and the reason I have given it, if you click it here, you will see that it is a huge file. I hope you could understand, it is a huge file. How big it is? For a average PDB file, if you copy the file and paste it to your Word or Notepad and make the font 10 to 11, you will get 50 to 60 pages. That is one of the reason a lot of people do not read the Pdb file, whereas Pdb file is not only, most of the people get the coordinate information. Definitely coordinate information is important, but Pdb file provides you much more than that. What we are going to take a look. So, this is the start of the Pdb file, and you see so many things. One, there is columns which talk about what is this. The header talks about the enzyme. If you see the type of molecule here, it is a transferase. So, deoxycytidine kinase is a transferase. The date of release. So, you deposit the Pdb information, they give you the validation report, but you could hold it. So, you could hold it for the publication to be accepted. So, finally, it was released in 3 Jan 09. The Pdb ID I talked about. The title, talk about the title of a crystal structure. Then the chain, it is the number of chain and chain name. This will tell how many polymers are there. 4 polymer, chain A, B, C, D, that like that. Scientific name of the organism from where the protein is coming. Deoxycytidine kinase, the human protein. So, it is Homo sapiens. Its common name is human. Where it express, the expression system. So, lots of experimental information is there. So, expression system is E. coli. So, though it is a eukaryotic protein, it is expressed in the prokaryote. The standard system we use is E. coli. All those information you could see. The journal, you will see the authors, the title. Why journal information is important? Because you know about a structure 3HP1, but what is the importance of the structure? What is that structure is talking about? You will get that information from the journal. So, you have to combine the information you get from the Pdb ID about the structure information and to go to the journal where the author write about the findings, why this structure is important and how this structure is used for further exploration of science. Resolution is very important. Why? I talked about that, but just to a quick refresh, if you see, this is the same structure, but we get it in different 1 angstrom, 2 angstrom, 2.7 angstrom, 3 angstrom, and you see when you get in 1 angstrom, it is so beautiful, it is so confident that it is easy to solve, and even a newcomer could model it using automated model building. Whereas, when you go to here, you have to use experience. So, high resolution structure is always easy, especially when you are going to look at the interaction between an enzyme and a substrate, or atomic level interactions are required. I do not want to complicate here, but sometime very high resolution structure below the number below 1.5 angstrom could be problematic because it has come with too much information. We all say that when you look at a crystal structure, it gives you a static representation, but now through the course I have talked about, you now understand that a crystal having a lot of water channel, the small molecule could change conformation. So, it is not exactly static, here the protein loops are moving and all. So, there are considerable flexibility, but when you are modeling, you prefer one high resolution conformation. With more high resolution, you might get too much information which you do not require. So, high resolution is always good, but too much high resolution could be problem. If you download structures especially below 1 angstrom, you will see a lot of alternative conformations when you go and see the electron density map. How we will look at? I will talk about this in the next class. So, coming to the unit cell parameter, which is called the CRIST. The CRIST information, you will see the record portion is says CRIST 1, you will get A, B, C, you will get alpha, beta, gamma, and you get space group. You need to understand something. If the structure was not determined by crystallographic means, what will happen? You understand the problem? So, you have seen that among 1,80,000 or 75,000 structures, nearly 1,50,000 structures of the protein are solved by X-ray crystallography. When it is the method of X-ray crystallography, you need these because you have to connect the closest point of the unit cell with the start of the coordinates, and that is why you need the CRIST, the ABC and alpha, beta, gamma, and you have to develop a matrix to do that. But what if, because we know that around 20,000 structures are determined by non-crystallographic methods, which is NMR or cryo electron microscopy. We have talked about them. So, what about them? Do they have CRIST? To maintain the format, they also have CRIST, but it simply defines a unit cube where A, B, C equal to 1 and alpha, beta, gamma equal to 90 degrees. The space group P1 and Z equal to 1. The Hermann-Mauguin space group symbol is given without parenthesis P21, 21, 2 and using the full symbol C121 instead of C2. So, what are they? So, here if you see P stands for primitive. Remember, we talked all those symmetry things in X-ray crystallography. So, P is primitive. 4 3 means like this, 2 1 if I write, now you will understand. So, it is the rotation and translation in different axes. 4-fold rotation followed by 3/4 translation, 2-fold rotation followed by half translation, this way. The screw axis is described as a 2-digit number. For a rhombohedral space group in the hexagonal setting, the lattice type symbol uses H. The Z value is the number of polymeric chains in a unit cell. So, there are Z values also, which is talk about the polymeric chains in a unit cell. In the case of heteropolymers, Z is the number of occurrences of the most populous chain. So, here we have one chain, one polymeric chain only. Now, I want to talk about a very interesting thing. You have learned 3 structure determination technique: X-ray, NMR, cryo-electron microscopy. Now, you know that you have around 1,50,000 structures determined by X-ray, other 20,000 by NMR and cryo. So, if I give you a PDB file, can you tell me the structure, if it is not written there, how the structure is solved? Can you tell me how the structure is solved? Is it solved by X-ray or cryo-electron microscopy or NMR? The first clue would be given from the crest. If the crest is not cube and the values are not exact, A equal to B equal to C equal to 1 and alpha beta gamma equal to 90, then you know that it is solved by X-ray crystallography, majority of the problem solved. Now, how to differentiate between NMR and cryo? If you remember, I talked about the fact that in NMR we do not determine the structure, we average the structure. So, if you look at the NMR file, you will see multiple models are there. Generally 20 models they represent, first one being the highest resolution. So, when you see more number of chains present, you will be sure that they are NMR. So, this is a very simple trick to identify between the PDB files of the determined by 3 techniques. Now, coming to the coordinates. So, as I told, the atoms would be defined by record, the atom serial number is there. So, these are atom serial number, but these are not residue serial number. What is that? Remember. So, when we talk about atom serial number, we are talking about the first atom. It might not be. So, if this is the protein, it could start from here, it could start from here, it could start from here. Anywhere it start, the first amino acid, its first atom have atom serial number 1, but when you come to residue serial number, for this it is 1, for this is 2, like 7, for this it is 23, in that way. So, if you want to know that the protein is fully crystallized or not, you cannot check the atom serial number, you have to check the residue serial number. Okay. These are the coordinates, these are chain identifier, this is the atom name, this is occupancy and this is thermal factor. So, first talk about these coordinates. This is where your atomic structure is. We will talk about this in details, but occupancy and thermal factors are also very important information provider. What is occupancy? Occupancy is mostly you could explain it in X-ray. Why? If you remember, X-ray is diffraction, right? So, if your atom is here and it diffract, so when you calculate the electron density, you get electron density in one point. So, the probability of finding the electron density is 1. So, occupancy is the probability of finding the electron density of the atom, which is ranging from 0 to 1. So, at lowest it could be 0, at maximum it could be 1. Okay. Why it is very interesting, as I told? So, if your proteins amino acid have altered conformation, suppose you have a serine, so CH2OH, if that serine have 2 conformation equally populated, the occupancy would be 0.5, 0.5. If one is more, is 0.7, 0.3. Now, here is a very interesting thing, and because we are talking about improvement of science, a lot of improvement could be happen in this area, which will give us idea about dynamics. What is that? And I am talking about only X-ray crystallography here. See, if you think you have one amino acid here and one amino acid here, like conformation. So, it adopt one conformation here and another one here, but how it goes from one to other? What I mean, if your proteins one amino acid have conformation A here and conformation B here, it should go from A to B or it should come from B to A. So, you should have some intermediate conformations also, and that is perfectly true. So, why it is not there? Because the software measuring have a cutoff and it would not provide you the measure where the contribution is 0.1, 0.01 or something. There is a lowest cutoff. But if you allow, if you develop a better software, you could identify other conformations which would be invaluable in understanding the dynamic nature of that residue. You understand what I mean? So, you could not only identify two conformations, you could also identify the transitions and some other conformations which take important part while this transition is happening. So, that is the importance of occupancy. What is thermal factor? Thermal factor gives you an idea about the disturbance present there. What I mean, if there is a loop which is very flexible, which is moving randomly, you are supposed to get high thermal factor. Thermal factor range from 1 to 100. Okay. As I talked about, there is a tar. The tar record occur in the coordinate section of the entry and indicate the last residue presented for each polypeptide for which there are coordinates. For proteins, the residue defined on the tar record is carboxy terminal residue, because it is N to C always. Then heteroatom, here also you get the record, you get the heteroatom serial number and ligand. First, tell me why we need atom and heteroatom. So, when you get here, you get the atom, you get heteroatom. What is the difference? Very, very significant. See, when you are working with a protein molecule, the protein molecule have 20 amino acids. When you work with a nucleoside, RNA, DNA, they have actually 5 different nucleotides. There are lipid molecules, there are carbohydrates. We have discussed them and you know all of them, right? So, is it possible to know about their bond distance, bond angle, dihedral and all those informations? Yes. All those informations are collected in a library. So, when you bring any protein, the protein's geometrical character is already there in the software in the form of a standard library. Clear? Suppose you are designing a new drug, you include boron as a part of the molecule. How the library would understand that? If the library have to cover all your imagination, then the library should include all the chemistry, which is literally impossible. You understand? So, atoms are the standard molecules which are depicted here. Heteroatoms are designed by us or some unnatural molecules where the geometrical parameters would be developed by you, and when you want to work with a software, you have to include those geometrical file in the form of chemical information file or crystallography information file to the software. You have to provide the software, that is called heteroatom. Then coming the record called connect. Connect defines the bonded interaction angles and dihedrals between the atoms of intra-protein residues or atoms of the protein residues with heteroatom. So, if you see, connect defines bonded interaction here, connect defines angles here, connect defines dihedrals here, but when I am showing you this is good for you to learn, you do not have to learn them. Why? Because now all the standard softwares, they already calculate this and take them immediately. So, you do not need to have a connect file, because the connect file would be calculated and created by the software. At the end of the Pdb file, you have to write END. So, what would be the potential use of this Pdb file? One, distance calculation. One can calculate distance between two atoms. How? So, if atom 1 have the coordinates x1, y1, z1, atom 2 have x2, y2, z2. If you go back with a quick, you will see that here you have x1, your coordinates y1, z1. This is x2, y2, z2. Then you get these values and you make this formula x1 minus x2's whole square, the distance, y1 minus y2's whole square plus z1 minus z2's whole square root, and you get the distance. So, what about the distance? One can calculate distance between any two atoms. Remember, this is 3D distance. What I mean by that? If you have a peptide like this, right, you could get the straight distance, right, if the sequence is like that. So, let us say this is the length, but this is now this. So, the 2D distance is 2D distance between A and B is this, but 3D distance between A and B is this. That is what is important here. It required for finding interacting atoms within particular angstrom range. One can write their own script or use existing tool from softwares like Pymol or Qt. So, what I am talking about? So, if you are looking at a protein and you are looking at the two residues, the distance would be calculated by this. How it would be helpful? When you see that you have a amino acid A and B, if this one have a C double bond O and this one have a NH, you could find the distance and talk about the fact that this is forming a hydrogen bond or not. In that way, many things could be attained by doing the distance calculation. Similarly, angle calculation, whereas distance calculation needs 2 points, angle calculation would be having 3 points, and you take 3 points P1, P2 and P3, which are having coordinates x1, y1, z1, x2, y2, z2 and x3, y3, z3. Now, you make vectors. A is P2 minus P1, which is Ax, Ay, Az. B vector is P3 minus P2, which is Bx, By, Bz. So, now the theta, the angle would be cos inverse dot product of two vectors and absolute value of the two vectors. So, why angle calculation is important? Sometime you want to take a look how the active sites or where the molecules are interacting, how they are coming, how the movement happen and all, and a angle calculation always help in that. Dihedral angle, there are many dihedral angles, but I will talk about phi and psi, but also side chain there are chi's. So, anything you could calculate. We have already talked about phi and psi. Phi is C I minus 1 N I C alpha I and C I. So, it is a torsion angle, and psi is N I C alpha I C I and N I plus 1. So, you could see the angles. So, the dihedral angle can be thought of as the angle between two planes. We have already talked about when we were talking about proteins. So, I am quickly going through. It is the angle from the planes containing A and B to the plane containing B and C. If you see here, it is the angle from normal vector A cross B to normal vector B cross C in A and N B counterclockwise around B, where A cross B and B cross C are cross products. So, by using those, we could now calculate distance, angle and dihedral angle, and this provide you to the ability to calculate everything. And as I told, what are the application? You could calculate the existence of a alpha helix. The criteria for alpha helix, a hydrogen bond is formed between I to I plus 4 or N to N plus 4, and the hydrogen bond is between residue 1's carbonyl with residue 5th amide. You have to find the pair of residues I and I plus 4 whose distance between O and N from main chain have distance less than 3.5 angstrom. Now, you check for residues I plus 1 and I plus 5 follows the same trend. So, if it happens, then you know that the orientation you are going through is representing a alpha helix. Just think about, by only understanding the distance calculation in 3D, you could have ability to write an algorithm which will represent a program to calculate the presence of alpha helix in a protein or not. Beta sheet, criteria for beta sheet: residue I in strand 1 forms a hydrogen bond with residue J in strand 2. The next bond can be formed in two different ways. Residue I plus 2 in strand 1 binds to J plus 2 in strand 2, which is referred to as the parallel beta sheet. Residue I plus 2 in strand 1 binds to J minus 2 in strand 2, referred to as anti-parallel beta sheet. So, you could do that. In addition, you could measure the angle, between I and J, where the hydrogen bond is formed. If the angle is 180 degree, it is a anti-parallel. By incorporating those logics in the algorithm, again you are going to have a program which could successfully calculate the presence of beta sheet. So, you could do that, but all those are very tedious calculations. If you could try, but please you should try, you try them, download the Pdb file, get the coordinates and try those formulas. The helices, the two strands, hydrogen bond criteria, other distances between ligand and enzyme, all these are very tedious calculation. So, it could be obtained by writing stepwise algorithms. You have to understand the logic and you will use logic to make logical reasoning. That logical reasoning would be converted to a program using any programming language. So, I talked about, but some of the popular packages are Rasmol, PyMol, CUD, VMD, Chimera, Swiss PDB Viewer. JMOL, MOE, SRView, a lot of them are there. Because I am taking your class, I would also love to introduce a software package currently developed by us, and we are working with this. My first PhD student Ghazal, she have already graduated working on. So, what is our aim is we are developing a package which would be making the non-computational user coming from core biology, giving a user friendly platform. I will talk more about this, but if you are interested, I have provided the link. You could see that. Just one thing, we have written this in C language, and currently this is the fastest parser present in the world. The calculation, the parsing, what we do is the performance wise is the fastest among the currently established softwares. What is parsing? I will talk little bit about, but before that, what are the problems in PDB? The presence of dummy coordinates, identical coordinates, missing coordinates are the problem. Atomic occupancy is larger than 1 or even negative, which should not be there. Atoms too close to each other resulting close contacts, breaking the rule of chemistry, which should not be there. Unnatural dihedral angles, use of different ligand names for water molecules H2O, WAT, HOH, etc. There should be one name. It is easy for the program. Presence of solvents which are there only because of experimental technique, mainly in crystallography. To get crystals, we use a lot of conditions, and that brings many ligands to be incorporated or involved in actual crystal structure. They are misleading most of the time. They are creating non-biological environment. Inability to accommodate larger structures with the current advent of cryo-electron microscopy. You have already seen huge structural assemblies are coming. The PDB format was created to accommodate crystal structures in 1970s. Very few or no one have imagined that time that cryo-electron could solve so big assemblies. Now, even crystallographic method have solved ribosome structures, and cryo is reaching with mega Dalton level. So, we need accommodate all those information coming from the larger structures, and there are many of them. So, how to solve them? Already PDB have introduced mmcif, as I talked about. They are also bringing mmcif, which are solution, but if some of you are interested to work with, you need a very good architecture. So, you have input, you have data structure hierarchy, where you have the polymeric chain, then in the next level residue, then in the next level heteroatom, then in the next level atom, and you could have developed data structure hierarchy. You could use existing data structures like atom bucket, KD tree, octree, and once you take the protein and develop this hierarchy, you have the input of the Pdb file, the architecture when it perform, that is called parsing. So, you have to develop a parser. This parser will take your protein, they will divide it into hierarchies, and that would make it easier to provide further outputs, right, like PDB remodeling, water detection, surface detection, comparison of sequence, and many more, many thousands of application is possible. So, that is one where there are a lot of scopes of future research, because with enhancement, with new techniques incorporating, we need to have some flexible architectures to come. And with that, I would finish today's description, today's class of PDB, with the news that we are celebrating 50 years of the protein data bank this year, and as you all know now, we have started in 1971. and in 2021 we are celebrating the 50 years of protein data bank. So, if you are interested, go to PDB, search celebration of 50 years of protein data bank, you will see a lot of programs, and because of the corona situation a lot of programs are actually becoming webinars. So, you could have take part in them, you could have gain further motivation through them. With that, again I finish this class. I again request you, thank you for listening, request you to continue listening to understanding, but at the end do by your own. Go to the PDB file, go to RCSB, download PDB file, do all the calculations. Once you do it by your own hand, you could have much more understanding. Thank you very much.